Welcome to Power Up, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on PowerElectronicsNews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for power electronics in markets such as automotive, industrial, and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of PowerUp. Today we will talk about silicon photonics and silicon carbide, energy efficient innovations. We will explore how smart SiC, the technology behind Soitec, enhances electric vehicle efficiency and reduces environmental impact. Additionally, we will delve into smart photonics SOI, which integrates cutting-edge optical functions with electronic circuits for high-speed data communications. Our guest is Christophe Maleville, Chief Technology Officer and Senior Executive Vice President of Innovation at Soitec. With a Ph.D. in microelectronics from Grenoble Institute of Technology and an executive MBA from INSEAD, Christophe has authored or co-authored more than 30 papers and holds 30 patents. Soitec is a semiconductor material manufacturer that is playing a critical role in the development of smarter, more energy-efficient cities and transport with its chemical manufacturing. So let's talk with Christophe. Hi Christophe, thanks a lot for being here. Thanks a lot for coming at Power Up Podcast. How are you?
I'm doing good. Very nice to talk to you tonight, Maurizio.
Thank you. My pleasure. Thanks a lot for your time. So where are you located, Christophe?
I'm located in France. The company is in Bernin, a small village next to Grenoble area, and in the French Alps.
Good. So today we will talk about silicon photonics and silicon carbide. Before that, so let's start with an introduction. So please give me an overview of Soitec and an overview of your background.
Yeah. So before jumping into Soitec, I'll start by myself. So I joined the company in 1993. The company was 1 year old with 12 people. There was the startup out of the Leti, and then I joined this company to start as a Ph.D. on wafer bonding process that now known as Smart Cut. At that time, there was a code name. And my PhD was dealing also with the integration of Smart Cut for the SOI process. Then I joined the company formally after the PhD, developer engineer, product VP, and then I had the ambition, let's say, to go for general management. So after MBA and a 2 years period as a Asia sales management, then I joined back the company in the headquarters as a general manager for the SOI business unit. And since 2019, I'm the CTO of the company. Talking about Soitec now, so Soitec is world leader in semiconductor material, a world leader in semiconductor materials. The Soitec technologies plays a key role in the semiconductor supply chain. We have set this new stop, I would say, in between the bare wafers makers and the IDMs. And the way I would describe it is that we are pre-installing performance and power saving active layers on substrates that become so-called engineered substrate. So what our team are doing, our teams are basically discussing with the system leaders, innovation platforms, and identify which material will best serve the future challenges that we have as users and that then the system makers are looking at. And we are integrating those materials as active layers in the engineered substrates. Then our customers are processing, patterning substrates, cut into the chips that we get then into all the objects we have on a daily. And to complete the picture on the supply chain, we of course collaborate with industry partners to create best-in-class solution for chip miniaturization, improving performance and energy efficiency. Improving energy efficiency is one of the key words for our development.
Thank you. Indeed, I have prepared two topics, as I mentioned at the beginning, silicon photonics and silicon carbide. So let's start with the first one. So silicon photonics is often considered as a breakthrough for energy efficiency in data centers and AI workloads. So what advances in specific in this technology do you believe will be important to meeting the growing demand of AI booming? And what is your activity in specific on it?
Well, I think that's a great question, which is in the actuality today, performance and energy efficiency around the AI. And I would say that many applications, and specifically the ones where we enjoy real-time performance, they rely on data with low latency and high bandwidth. Silicon photonics really is playing this key role in low latency and high bandwidth for the data. And since a few years, that silicon photonics gained maturity with the deployment of connectors for the servers. So these pluggable connectors to have the fiber optics going directly at the back of the blade has been the first development. And with that platform, the 300 millimeter monolithic silicon photonics technology is now offering both photonic and electronic on a single chip. And this is reducing the cost and the power consumption while improving the performance for AI. For example, it enables high-speed data transmission exceeding 100 gigapascal per second per channel, but also a large bandwidth, which is ideal for the AI workload. Going further, we look at how to enable the so-called coplanar optics, which will more improve the situation. Then photonics chips would then directly integrate compute and switch ASICs, which is further reducing latency and power loss over what we have today as the pluggable interconnects. Then to make the link, what we are doing into this arena. Well, we provide the base material for this silicon photonics implementation. And so we tune the silicon thickness and the oxide thickness of our SOI silicon and insulator substrates so that we can bring together the coupling of the fiber optics and the typical wavelengths that is used together with the best possible interface quality to avoid any loss into the light and get the best performance into the component. So when we are developing energy efficient applications requires, but this is in general for each technology, a number of challenges, technical challenges. So from your perspective at Soitec, so what are the most significant obstacles that you see in scaling silicon photonics for a broader or other semiconductor technology for a broader, wider adoption? Yeah, so thinking about the technology, the one important element is the thermal management. This is one of the major challenge to manage this heat generated by high-performance silicon photonics device, especially when they are integrated into very dense, packed data center environment. So this is number one point. Number 2 point is supply chain complexity. There are challenges when looking at the global supply chain constraints, securing high quality materials and advanced material capabilities. So one way is standardization and what I would call interoperability, making sure that silicon photonics components are compatible and can integrate with the current data center infrastructures and the AI platforms. We need to have that to make it easier implementation. And in there we are triggering a lot of collaboration, which is key, scaling the technology and meeting the demand. Last, which is the one very important from our side, is the material optimization. Well, all the advances in the substrate materials, like the one we are developing, very crucial for improving the performance and the energy efficiency of the silicon photonics. Per se, the silicon photonics is a gain into energy efficiency because we move from electron generating heat to optical fibers where there is much heat generation. But then we are also working on limiting the heat generation in terms of the device by improving the material, platform after platform.
So let's talk now about silicon carbide, so wide bandgap material. So I'm trying to write about the wide bandgap on PowerElectronicsNews.com. I'm a supporter of wide bandgap. So let's talk about silicon carbide. What specific challenges in power conversion for the electric vehicle industry led to the development of smart SiC, smart SiC, and how does this technology address these challenges?
Well, you're right. There's a lot to say and a lot to do with compounds and wide bandgap regarding the power devices. Also in the RF, but let's concentrate on the power devices today.
Sure.
So traditional silicon devices, typically IGBTs, well, no question they deliver device cost that is typically 3 to 4 times cheaper than silicon carbide as it is today. But silicon carbide brings a huge benefits in terms of energy efficiency. So typically the gain is going to be at the system level, and you will gain in terms of the number of batteries you have to put into the car, which means then gaining into the weight of the car and gaining also into the charging time, into the energy efficiency. So that's key. So it's like silicon carbide is a more expensive device as of today than silicon, but brings tons of benefits in terms of the system level, so in terms of the car. The reason is that the energy efficiency that silicon carbide brings is critical to have a longer driving range, reducing the heat generated, and minimizing, again, the system cost. And the next generation after generation EVs, they require really more compact components, efficient and sustainable. You know, like many people, I'm to share with you this story. I'm looking now at electric cars, which is the best, and so on. And it always comes down to the weight, the range, and the charging time, and how this is going to impact your new life as you move into electric vehicle, and how you will be able to do it. Yes. So, well, silicon carbide brings an advantage, as I say, but still suffering from the cost and still suffering from quite a lot of CO2 generation while building this low productivity, I would say, crystal. And smart SiC will improve this situation. So first of all, what we do in a nutshell is that we take this very unique crystal, which is silicon carbide with its native energy efficiency, and we cut it in a super thin film, half a micron, and we transfer it to a polysilicon crystal based material, trying to extract the best of silicon carbide. So the mono silicon carbide, this pure crystal that we transfer, brings the energy efficiency and the epi ready for the device layer. And our polysilicon carbide can be doped 10 times, 20 times more than silicon carbide and bring much more conductivity to the vertical device. A silicon carbide chip is a vertical device. So it will go from this mono silicon carbide we transfer down to the backside of this high conductivity polysilicon carbide. By doing that, first of all, we use 10, 15, 20 times the same crystal, the same wafer at the beginning, which is then improving by 70% the CO2 emission to build this silicon carbide. And then, thanks to the conductivity, we enhance the device performance and then can get at least one generation gain in terms of the energy efficiency. Okay, then some other performances like higher production yield, smaller dies, because when you bring more current per die, you can make smaller dies. And then at the end, we can envision lighter and more efficient EV components. Less CO2 again and less cash injected because a better usage of the existing crystal.
So let's talk about collaboration. So which are your collaborations involving smart SiC? What are your plans to expand the adoption of this technology?
Well, today overall, we are actively engaging in more than 35 collaborations, meaning 35 customers evaluating, qualifying, testing, designing with our technologies to accelerate the adoption of the smart SiC in power electronics. And our focus is to expand into the market globally, of course. So if you look at the recent announcement, we announced a partnership with Resonac in Japan to enhance efficiency of 200 millimeter SiC wafers. Resonac is a supplier of a high-quality monocrystal. They have a small production of high quality and also of epitaxy processes. And combining with our proprietary smart cut technology, we can create a lot of engineered substrate that will demonstrate device performance and manufacturing yields. We here combine high quality silicon carbide with the smart SiC to generate many of them. And on top of that, working with them, we can integrate high quality epitaxy. Of course, our team we work closely with ST Microelectronics. This is the leader of silicon carbide technology in your country, Maurizio. So I think you know them very well. And we are also collaborating with X-FAB to qualify smart SiC at foundry level. In addition, what to say, we opened our new fab in September 2023, and now we are ramping up production, of course, to meet the growing demand of our wafers. And very important to have the complete picture of the supply chain. We are qualifying multiple suppliers, publicly announced Mersen and Tokai Carbon, which are supplying us high conductivity polysilicon carbide. This way, we can have a diversified and stable supply chain to support the seamless adoption and widespread of smart SiC.
Good. So this is great. Thanks, Christophe. So I have just the last one before concluding this great podcast. So we talk about sustainability, energy efficient solutions. So as the demand for sustainable, energy efficient solutions in different markets, data centers, automotive, would increase. How do you envision Soitec's role in pushing forward next generation semiconductor materials and design that would prioritize these two topics, as I said, sustainability, but also without sacrificing performance? That is important.
Oh yeah, that's very important. I may surprise you, but I don't consider that we have necessarily to sacrifice on performance to go into the sustainability. And I think here, coming back on our unique smart cut process, we typically have one or more degree of freedom in designing the substrate, because if you use a monolithic substrate, well, you use the surface only. This is number one, and then you have to cope with the properties, the physical properties of the substrate on its wall, in terms of dealing with the thermal management, the conductivity, and so on. In our case, we really disconnect what is the active layer and on what type of substrate we can bring it. And we have more degrees of freedom because we can also put additional active or passive layers in between this active layer and the substrate, for example, to account for different wafer bonding properties, or to deal with the difference in the CT, the thermal expansion coefficient for the materials that can be very different. So by doing that, by first of all, by transferring thin layers from one given wafers, we bring a big advantage in terms of sustainability. Most of the time, the growth of the crystal happens at quite high temperature, and by being able to reuse this substrate multiple times, this is a huge advantage. Then performance-wise, well, we bring it to what makes sense. I can take an example, which is FD-SOI, for example. In FD-SOI, we take a very thin layer, a few atomic layers, and we transfer them onto oxide onto silicon wafers. These structures we are bringing to our customers allows them to make this the channel of the transistor in an undoped way, because we have a very well-controlled thickness and doping of that layer, which then allows to make devices that can be always on, meaning able to wake up, do the job very quickly, very fast wake up, and then go back in the sleep mode. So meaning being in a low consumption by design, but being able to have performance on demand very quickly. So this is typically the kind of a device we are thinking about for the Edge AI generation, where what you need is to have at your wrist, in your phone, in your car, in your house, devices that can wake up, do the job, and be in a low consumption mode, but deliver the high performance, even talking about RF and bringing you the results without having any cloud communication and latency, because as fast as you can make your cloud, you will have latency by centralizing the information. So the simple applications we need to have on this type of low power. Another example is in the filter. We are now transferring piezo material onto silicon. And by doing that, the ultra thin film we have for the piezo material will not shift because of temperature, because we all know that our phones are heating up when we are extensively talking and getting data and so on. And this heating can degrade the performance, but having it as a thin film onto silicon allows to keep the temperature stability from the design, and then to keep the performance in the filters. Tons of examples like that we can do with the GaN, we can do with indium phosphide, all the families of silicon I mentioned, silicon carbide, we talk about it. So we develop a comprehensive table of what we call anything on anything, where we are always looking at what's the best active layers to have the sustainability, of course, using multiple tidal crystals, improving the supply of this crystal at the end, and look at the best performance in terms of the performance of the device itself, the frequency, the speed, but most importantly, the energy efficiency.
Really nice technologies and a really nice future. Thanks a lot, Christophe. Thanks a lot for joining us at PowerUp Podcast. Stay in touch and see you next.
Yes.
Thank you.
Thank you very much.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio, and the producer is James Eade.